Hopefully, okay, I think I see that they're sharing. Awesome. So super excited to have you all joining me today, whether it's morning or afternoon or evening. I really appreciate you. And I am super excited to talk about a topic that's near and dear to my heart. So talking about dyes and their sustainability. So first things first, I like to tell you a little more about myself. I'm not going to touch on all of these points because Nim just touched on them. But by training, I identify as a dye chemist. I've held various roles, as was mentioned before. So some of the companies I've worked with are American and Efort. They make threads. We're probably making their thread, or excuse me, we probably are wearing their threads. They're a global company, and I worked in their dyeing and finishing plant. I've also worked at Cotton Incorporated. So various roles in such a short amount of time between when I finished my PhD and now. And now I'm the principal investigator of the Sustainable Dye Chemistry Laboratory. I'll talk a little bit more about what my lab does on the next slide. And I am an affiliate of the BioColor Consortium, which is a global group of researchers dedicated to exploring natural or bio-based dyes as synthetic dye replacements in industrial dyeing processes like textile dyeing. So as promised, what does my lab do? In a nutshell, we design and develop dyes, ideally dyes that are environmentally benign. And we also care about the way we apply the dyes or the coloration methods, making sure those are also environmentally benign. So we do a little bit of basic research as well as applied research. And so developing the dyes themselves, designing and developing them. So something we are just starting out to do as a lab, and my lab is just a little over a year old. So a lot of our projects are new, I should say, working with biosynthesizing dyes, and we're doing this with a lab in the chemistry department at North Carolina State University. So my lab is housed in the textile engineering, chemistry, and science department at NC State. So once we have the dye, then we care about looking at the dye properties. So one thing we really care about is toxicity. So does the dye have the ability to cause cancer? Can it be mutagenic or cause a change in DNA? We care about the substrate that we're applying the dye to. It's going to influence how it interacts. So if the substrate is very porous, then dye can diffuse within. We also care about dye substrate interactions, especially dye uptake or how much dye goes onto the substrate. Ideally, we want most of the dye on the substrate, not in the wastewater. And then ultimately, once we've explored these things, we want to apply the dyes in a textile dyeing process, a hair dyeing process, or whatever coloration process. One thing we are just starting to do is finding ways to apply dyes in CO2, so carbon dioxide, as a waterless dyeing method. And so we're looking at applying some natural dyes in that particular medium. So stay tuned for our work in that area soon. So let's talk about dyes. First, color. So look around, color is everywhere. We use color for various reasons. Number one, aesthetics. So to give our Ferraris a red color, and Ferrari red is an actual color name. To make our houses stand out from others, to make a fashion statement with our hair, and even our clothes, to designate certain items as certain items. So our jeans are typically blue. Our bananas are typically yellow, blueberries blue, to help us see seasonal changes. So when we go from fall to fall to winter to spring, it can also give us protective functions. If you think about the chameleon being able to change colors based on its environment. And then also it can help us establish order in our lives. And we think about a traffic light. So, you know, green means go, yellow for some means speed up, for others it means slow down. And then red means red, or stop, I should say. How can we obtain color? The main way we can obtain color is through application of colorants, so dyes as well as pigments. And I'm showing the main differences between the two. Not going to go through all of them because of timing, but with our dyes, we can get all colors except white. With pigments, in particular, inorganic pigments, titanium dioxide, we can actually get white as well. Dyes typically can go into the substrate, but pigments are typically applied on the surface, and then we find a way to fix them there or anchor them there with a binder. There's a way during the polymer, when we make fibers, to be able to get pigments inside during that fiber formation process, but typically the pigments are applied on the surface. The big difference, especially from the dye chemist point of view, is solubility. Not everyone recognizes this definition, but for me, I recognize it. So dyes are typically soluble in the medium they are applied in. Typically, this is water, especially for textile dyes. Pigments are typically insoluble in the medium in which they are applied. What makes a chemical a dye? So not every chemical is a dye, but every dye is a chemical. So they must contain or exhibit the following. So a chromophore, at least one, an oxychrome, extended conjugation, resonance, as well as the ability to absorb in the visible region of the electromagnetic spectrum. And so the visible region is a very tiny slither, roughly 400 to 700 nanometers. And that's where we as humans can see color. So on the right, I'm showing one of the dyes I synthesized. It was one of a series of dyes, and each of them were red, and they absorbed roughly near 514 and 542 nanometers, making them a red dye. Now, I want to highlight typical chromophores and oxychromes. So chromophores really are the main group that help a dye be a dye. Most of the action, the absorption of light is going to happen at the chromophore. And one typical chromophore is the azochromophore, which I'm showing in blue. And then I'm showing a dye that has that chromophore. Anthraquinone-based dyes, we can actually see this chromophore in both natural and synthetic dyes. With chromophores, we just see those in synthetic dyes. And so I'm showing the anthraquinone chromophore in yellow, and then this chromophore in one of in a dye. Oxychromes, these are they can be found somewhere in the dye, and they are electron withdrawing or donating groups. And so I'm highlighting two. So the sodium sulfonate and the sulfonic acid group help make dyes water soluble so that we can apply them. In the case of some dyes like this one, which we can apply to polyester, which is hydrophobic, these dyes have very limited water solubility, and so we typically add a surfactant in the bath or the medium, or as part of the medium, to be able to apply these dyes to polyester, acetate, and other hydrophobic fibers. How do we classify dyes? Various ways. I would say the number one way is by origin, so whether it's natural or synthetic. And synthetic dyes, they dominate the market for textile, cosmetic, food, and other dyes. We can also classify dyes based on their chemistry, so by their chromophore as an azo dye, anthraquinone. You may have heard dyes classified as flavonoids, anthocyanins, so various chemical groups. We can also classify them based on application. So for textile dyes, there are various names or subclasses. And so dispersed dyes, I'm going to go back a slide. This dye is a dispersed dye. We disperse them in solution because technically they have very limited water solubility. We'll use a surfactant to do that, but we apply them typically to polyester and acetate. Hair dyes, they're designated based on their permanence. And so temporary dyes, they only offer temporary color, while permanent dyes can offer more long-lasting color. And side note, the database that Nim mentioned, you can scan this code to access it, but it contains several of these hair dyes. And I'm going to highlight the permanent dyes. They're a little bit unique in that instead of showing the final structures, because they can vary, I'm highlighting the precursors that you use to form the dyes in hair. We'll talk about that a little bit more on the next slide. Another group of dye application class I want to highlight are the FD&C dyes. You might have heard these dyes. So FD&C Red 40, big dye, it's in Kool-Aid and other products. FD&C stands for Food, Drug, and Cosmetics. These are dyes that are approved by the FDA for use in food, drugs, and cosmetics. How do we apply dyes? We can apply them directly as is to the substrate, or we might need to modify their structure or form them in the substrate. It just depends. So I want to highlight permanent hair dyes. We form them indirectly. And so what happens is you have small precursors or starting materials like paraphenylene diamine that can react with other precursors like resorcinol and do what I call join hands. And this all happens inside the hair fiber, which is pretty unique. So if you've ever used a permanent hair dye, you're doing chemistry on your hair. You can form dimers or two that come together, trimers, tetramers, etc. And ideally, these are inside the hair. This process is driven by using, for example, hydrogen peroxide and ammonium hydroxide to help activate the hydrogen peroxide. So let's shift gears and talk about the sustainability of dyes. And I want to address why I named my talk the way that I named it. So why is green still the new black? That should be why is green still the new black? A little bit of a grammar mistake. So dye sustainability, it's been on our radar as dye chemists for a while. It's nothing new, trying to make more sustainable dyes and coloration methods. A lot of research has been done, but the truth is more research still needs to be done to enhance or improve the sustainability of dyes and the way we apply them. So that's why I chose this talk, chose this title for this talk. So I believe there are 3 factors to consider when you want to assess the sustainability of a dye. So number 1, the ability of the dye itself to cause a toxic effect. Number 2, the sustainability of the method to produce the dye or make the dye. And then 3, sustainability of the method to apply the dye. A lot of emphasis has been focused on number 1, but I think 2 and 3 are equally important. So in the next few minutes, I want to briefly go over each and give some examples of how this has been addressed. So number 1, ability of the dye to cause a toxic effect. If there's anything you want to take home from my message today to spread to others, it is natural does not mean safe. This applies for dyes and other chemicals. So I'm showing one example of a natural dye, imidin. It's a fungal-based dye. And it can metabolize or be converted into mutagenic products. I'm showing them here that can cause a mutation or a change in DNA. So ultimately, this dye can be mutagenic. And so this highlights one example of natural does not mean safe. There are many other examples. I just chose this one. On the contrary, I want to show 2 examples of dyes that I synthesize that are not mutagenic. They don't cause a change in your DNA. These 2 dyes here, and they're among a group of dyes that I'm actually studying in my lab now to try and form larger structures or mimic the permanent hair dyeing process. I'll talk about that in a few slides from now a little bit more. I'm doing this work looking at the toxicity of my dyes in collaboration with a lab at Unicamp, Dr. Gisela Ambrosero's lab. So Unicamp is in Brazil. So how has this been addressed? in a nutshell, removing certain dyes off the market, or at least the precursors to some of the dyes, and then redesigning the dyes to reduce a toxic effect, whether it's genotoxicity or skin sensitization potential, you name it. So I want to talk about certain benzidine-based dye precursors. It was discovered that benzidine and certain derivatives could cause bladder cancer in individuals. So I'm just showing 3 examples of precursors that have been banned. There's a whole list of them. This particular dye is a dye that we can apply to cotton or cellulose. It's a black dye, and our liver enzymes can break down the dye into multiple parts. The starting materials to the dye, including benzidine, which can be converted into a reactive species that I'm showing here, the nitronium ion, that can react with DNA. It's a big problem, right? Well, there has been work done. This work was done in roughly the 80s by my advisor, Dr. Harold Freeman, my PhD advisor, where they looked at substituting out benzidine with this bipyridine group that I'm showing here in yellow to ultimately reduce the genotoxicity of the dye. There have been other studies that are similar in this respect. I just wanted to highlight this one. Regarding the sustainability of the method to produce the dye, I think it's important to highlight, a major issue is with the synthetic dyes, and so how they are created. And so synthetic dyes, they dominate the market, and we can get them on the ton scale. They're used on the ton scale, so a lot of dye. The major issue is we use petroleum to create these dyes, and we don't know how long, we're going to have petroleum around. And so I'm showing the reaction scheme to form the starting materials for, sorry about that. Let me go back here. Accidentally. I don't know what's, okay, I guess that's not me. So hopefully you can still see my screen. I'm showing how you can literally go from benzene to form a reactive species that we call diazonium salt that we can add to this particular compound, which is a naphthalate ion, and couple it and ultimately form an azo dye that's acid orange 7. So this is just one synthesis route. I want to emphasize that benzene is carcinogenic. That's another issue with this particular synthesis. So the fact that we're relying on petroleum-based starting materials, and we may not be able to do this chemistry, 100 years from now. So we need to find ways, alternative ways to create these dyes if we still want to use them. And then the fact that sometimes toxic products are used in the production process, like benzene. Okay. I'm not sure how to get rid of this, and I don't know if I did it or, let's see. Hopefully it's not too much of a distraction, the different lines.
Sorry,
okay.
I think this is a Zoom glitch. I'm trying to solve it on the back end.
Okay, no worries.
Yeah.
I was just like, did I do that? Okay. So I'll keep talking. So how has this been addressed? It's really something that's emerging, I would say. So there's an emerging interest to bioproduce dyes, or to use nature, biological systems like E. coli to be able to produce dyes within. So one example is carminic acid. It's a red dye that's found in food as well as other products. We get it from the cochineal insect, but the idea would be to be able to increase its yield, for example, to make it ourselves using nature as a resource and not petroleum as a resource. One of the biggest challenges with bioproduction is, one, you need a good idea of how nature makes this dye in the first place. And then another challenge, and that's not always easy to know. That's really not easy to know, I should say, And another challenge is being able to produce something on the ton scale to be able to compete with the synthetic dyes on the market. Okay. So lastly, I want to talk about the sustainability of the method to apply the dye. And I want to talk about this with respect to textile dyes. These dyes are often used with large amounts of water, energy, and other materials to help promote the dye to go onto the substrate. Those auxiliary chemicals can be toxic to, for example, aquatic systems. So sometimes excessive amounts of salt, sodium chloride are used, and other chemicals. So I'm showing here on the right this dye, which is also, you can also apply this dye to cotton. This dye on its own has very limited what we call wash fastness, or it can easily be removed when you wash your substrate that has this dye applied, so cotton textile. But you can add a copper sulfate treatment as an after treatment. So after you've dyed the fabric, you can apply this copper sulfate to it to metal complex the dye and ultimately create a dye that has better wash fastness. But on the downside, copper sulfate negatively impacts aquatic systems. So there's a trade-off. So what's been done to address how to apply the dyes? Just one example because of time. Replacing heavy or toxic metals that might be used like as a copper after treatment. Some dyes are actually applied as metallized dyes. So I'm showing two examples here, and I'm showing that, copper sulfate versus, for example, iron, using an iron metal ion, the toxicity is much less. So the higher this value, this EC50 effective concentration, the greater the less toxic it is. So basically, it takes more of that dye to cause such an effect. Okay. So what has my lab done? What are we doing now? We are looking at certain dyes as ligands that you can ultimately complex with environmentally benign metals such as aluminum and iron to form these metallized dyes in hair, which are larger in molecular weight. So if you remembered my slide about permanent hair dyes, we build them inside the hair fiber. The concept is pretty similar, where we're building these larger structures in hair that don't easily come out and make the dyes, permanent. And I put that in quotes. So depending on the metal that you use, you can get red or brown or other colors if you use other metals. And then also changing out the dye itself will help you to see other colors. So it's pretty cool. But what we found is that we can form these dyes inside hair under mild conditions, so roughly 40 degrees Celsius. Where to go from here? The United Nations, or the UN, has tasked us with some sustainable development goals to achieve in the next few years, one of which relates to textile dyeing and other dyeing processes. And that is related to, for example, clean water. Responsible consumption and production is also lumped in. And there are various green chemistry principles that can be applied to help tackle these issues that I just mentioned briefly about dyes and their sustainability. And so I believe educating, not just at the higher ed level, but K through 12, start introducing concepts such as, natural doesn't mean safe. We can't make blanket statements that, all natural chemicals are safe without having that data that shows indeed that it is safe. And I think, spreading this knowledge to the um, general public is also necessary to also reshape their thinking about the use of natural dyes in our products. And then I also think educating from the perspective that's a little bit more holistic, that accounts for not just the dye itself potentially being toxic, but also, making sure the way it's produced is sustainable and the way it's applied is also sustainable. So with that, that wraps up my presentation. I hope you learned a thing or two, and I'm happy to answer any questions.